The students who are having any query on Powell's method, they can ask. Okay. Okay, so welcome to uh, the next lecture on optimization problem, which are having multiple variables. And till now we have discussed direct search method, and today we are going to start gradient based methods. Okay, so I hope the discussion which took place yesterday, that is Powell's method, it was well clear to all of you. And today itself, in when we will be discussing this first gradient based method, that is called Cauchy method or C-best descent method, we will be discussing this particular method based on the problem which we took yesterday. So yesterday we took one problem, that is fx equal to x1 minus x2 plus 2x1 square plus 2x1 x2 plus x2 square, and your starting point was x1. For convenience, we took a starting point x1 equal to 0 0. Okay, so you can take any arbitrary point as a starting point, but for convenience we took it as 0 comma 0. Okay, so we will continue this problem to solve using your Cauchy method. Okay, so under gradient based method, as we know, as the name indicate, obviously we need to calculate the gradient of the given function. Okay, so how the gradient is calculated? Okay, so suppose we have a function fx equal to some ax1 square plus bx1 x2 plus cx2 square. We always have functions like this where there are several variables, or there are more than one variables. Okay, so suppose we have a n dimension uh, n dimension function, and if we want to take the gradient of this function, what will be the gradient? We will take partial derivative of your given function with respect to each variable. Okay, so suppose here variables are n variables x1, x2, x3, x4, and xn. So if we take the partial derivative, then this will be a column vector. The partial derivative will be del f over del x1, del f over del x2, similarly del f over del xn. Okay, so if you try to see the meaning of this gradient in graphical mode, suppose you are having some function fx which is drawn here graphically for certain value, say this is for a, this is for b, this is for c, this is for d, this is for e, this is for f. So you are having a function fx which you have plotted like this. This suppose this is a quadratic function. Okay, so you will have the plots of your function like this. The respective shape you are able to see. And if you want to take gradient of any at any point, suppose I want to take a gradient at point 1. So obviously the gradient will be normal to this particular surface. So if I take gradient at this point, this gradient direction is represented by 1 comma 1 dash. Okay, so this is the gradient direction for uh, at point 1. Similarly, the gradient direction at point 2, this is the gradient direction for it at point 2. So this will be 2 comma 2 dash 2. Okay. Similarly, for at point number 3 we have gradient this, then at point 4 this, and at point 5 this. So we can say that there is small change in your values of variable, but there is significant change in the direction of your gradient. And from the optimality criteria, we know that at optimum value of your variable or optimum value of your function, the gradient should be equal to 0. Okay, so suppose I have some value, say gradient. Suppose I take gradient at this point, have some value. So this may be, say, minus 10 to minus 8. Okay, because this will be a column vector. Okay, so then I have a certain value at this is corresponding to 1. Suppose we have value corresponding at point 2, so this may be 20. So what I mean to say, that if you are taking gradient and if you are comparing the values of gradient at one point to gradient at point 2, there may be large variation with the small increment or decrement in the value of your given variable. Okay, so that is why if we are searching the solution in the appropriate direction or the right direction, there are chances that we will get the solution more faster as compared to directions methods. Okay, so let us try to understand how we are going to implement this gradient based methods. One of the method that we are going to discuss today is the CPEST descent method. Sometimes it is also commonly known as Cauchy method. So if it is in examination, if it is written as solve the problem using Cauchy method, then you have to follow the same method. Okay, so in CPEST descent method, we choose one arbitrary starting point, that is the step number 1, and we set your iteration number I equal to 1. Then we find the search direction. How we find the search direction? So the search direction is found is given by Si equal to minus gradient of Fi. So it means that suppose we are at step number 1, then we are searching the solution in the direction of your gradient. Okay, so this is representing gradient of Fi corresponding to the value of values of x corresponding to xi. Okay, so this will be minus gradient of fxi. Now we need to determine the optimum step length. If we have find out the search direction, what we will do, like previous example, we will decide the optimum step length in the search direction, and we will equate the value of lambda I. And when we are able to, how we will calculate the value of lambda I, we will have certain function f f over del lambda, we will equate it equal to 0 to calculate the value of lambda, optimum value of lambda. So we will calculate the value of lambda I, and some value will come, and accordingly we will calculate the new point, not new optimum point, which will be xi plus 1 equal to xi plus lambda I plus si. Okay, put the value of si from here. So this will become xi minus lambda I into gradient of fi. This is quite simplest method, I think, among all the method which we have discussed. Only these three steps, a simple step, you need to remember, that you will have some arbitrary starting point, and then you will decide search direction, and obviously it will be based on your gradient. So this is minus gradient of fi. Then you decide your optimum step length lambda, and equate the calculate the next optimum point, which will be xi equal to xi plus lambda I si. Test the dew point xi plus 1 for optimality. If xi plus 1 is optimum, then stop the process. Otherwise, go to the step 5. So in step 5, what we are doing, if it is not optimum, we will set I equal to I plus 1, and again repeat the process from step number 2. Okay, so there are only, you can say, 2-3 steps involved in this Cauchy method or steepest descent method. Okay, let us take the example which we took yesterday. Uh, the example was minimize the function x1 x2, which is x1 minus x2 plus 2x1 square plus 4x plus 2x1 x2 plus 2x2 square. Okay, so since sorry, this is not Powell's method, this is using steepest descent method. Okay, so using steepest, because we have already discussed this problem using Powell's method. So now we are going to discuss this method using steepest descent method. Okay, so as the steepest descent method is based on your gradient, so what we will do, first we will calculate the gradient of your given function. So partial derivative of function with respect to x1. So if you take the partial derivative of this function with respect to x1, this will be 1, this will be 0, this will be 2 into 2 4x1, this will be 2x2, this will be again 0. Okay. Similarly, we will take the partial derivative of your given function with respect to x2. So x2, this will be minus 1, this will become 0, this will become 2x1, this will become 2x2. Okay, so this is your value of gradient of your given function. Okay, then you will calculate the value of gradient at your starting point. Yeah, gradient of f1, value of gradient at your starting point, that is the fx1. So this will be gradient fx1. Put the values of x1 in this gradient value. So x1 is 0 as well as x2 is 0. So all these terms will be eliminated, and this will become 1 minus 1. So this is how we have calculated the value of gradient at point x1. Okay, or the set of values, set of variables at starting point. Now what you will do, you need to decide your search direction. So what will be the search direction? Initially your search direction will be s1 equal to minus gradient of f1. Okay, so what is the value? This is 1 minus 1. So if you take again one more minus, so this will be minus 1 1. So this is now our search direction. I hope up to this point there is no doubt. Okay, so now what we are supposed to do, we are supposed to, since we have identified the search direction, we need to identify the optimum step length in this particular search direction in order to get the optimum value or the lowest value in this direction, in this search direction. Okay, so since s1 is equal to minus 1 1, so we need to find out optimum step length. So this will be fx1 plus lambda s1, lambda 1 s1. So this will come, x1 is 0 comma 0. Okay, x1 is your 0 comma 0. So this will remain if you multiply s1 by lambda, so this will become minus lambda, and this will become lambda. Lambda 1, lambda. So the values of function which we need to calculate, this will be f minus lambda 1 comma lambda 1. Okay, if we put these values in your given function, that is x1 minus x2 plus 2x1 square plus 2x1 x2 square plus x2 square. So if you put these values, this will come lambda 1 square minus 2 lambda. Okay, so in order to calculate the optimum value, what we need to do, we will simply take the derivative of uh, your given your new function, that is lambda 1 square minus 2 lambda with respect to your lambda 1, and equate it to 0. If you take the derivative, what will be the value? This will be 2 lambda 1 minus 2 equal to 0. Okay, so uh, it means you can easily calculate that lambda 1 is equal to 1. Once we have calculated the value of lambda 1, we can easily calculate the value of your next point, that is the next set of variables, this which will be x2. So this will be x2 plus lambda 1 si. Okay, so put these values. So this is 0 comma 0, x1 is 0 comma 0, lambda is 1 into s. What is s1? S1 is minus 1 1. So we have next set of values, that is x2 is equal to minus 1 1. Now what you need to do, because for optimality criteria in gradient based method, we will check that gradient of any function should be equal to 0. Okay, so if you take calculate the gradient of function at x2, so gradient of function at x2 you can calculate by putting these values, that is minus 1 1 into this particular gradient function. So this gradient function is 1 plus 4x1 plus 2x2. This is minus 1 plus 2x1 plus 2x2. If you put these values of x2 in this particular function of gradients, you will get these values. Gradient of fx2 is coming minus 1 minus 1. So as I told that for optimum value, the gradient should be equal to 0. So it is not equal to 0, 0 comma 0. So it means your x2 point is not optimum. You need to further explore the possibility to get the optimum solution. Okay, so till now we have x2 equal to minus 1 plus 1. Okay, and what, since we have not got the optimum value, what we will do, as per algorithm, if it is not optimum, we will go to the step number 5. And what is the step number 5? Set the new iteration I equal to I plus 1. So now I will become 2, and you will repeat the step 2. So now you will search the S2, that is search direction in at second point, and this will be equal to minus gradient of F2, that is the value of gradient at point 2. So let us calculate the value of gradient at point 2. This is minus 1 minus 1. So your new search direction will become S2 equal to minus gradient of F2, and which is equal to 1 1. Okay, again you will repeat the same process, that is you need to calculate uh, the optimum step length, that is lambda 2 in the search direction S2. So your search direction is this, and you have some values of x2. So this will be x2 plus lambda 2 s2. So if you solve it, your values will be a function of minus 1 plus lambda 2, 1 plus lambda 2, minus 1 plus lambda 2, and 1 plus lambda 2. If you put these values in your given function, you will get this expression. Okay. So in order to calculate the optimum step size, that is lambda 2, what we will do, we will take derivative of function with respect to lambda 2. Okay, so this will be 10 lambda 2 minus 2 equal to 0. This will give you that lambda 2 equal to 1 by 5. Okay, so I hope because this process is being done repeatedly, I hope there is no doubt to any one of you that how we are calculating the value of lambda 2. After calculating the value of lambda 2, you will calculate the value of your next point, that is x3, and x3 will be x2 plus lambda 2 s2. So if you put these values, this will come around minus 0.8 and 1.2. Again, you need to calculate the value of gradient at point 3. So if you calculate the value of gradient at point 3, you will put the value of x3 in your given function. If you calculate this value, so this will be your gradient f3, and this will be 0.2 minus 0.2. Okay. So this way, because again, our optimality condition, what is our optimality condition? We will stop only when we find out that the gradient of fi is equal to 0, comma 0. Okay, because this condition is not satisfied, so we can say that we need to proceed further. We have not reached the optimum value. Okay, so how we will decide the search direction? In this case, your search direction will be S3. S3 will be sorry. S3 will be minus gradient of, this is iteration number 3. Now our I is equal to 3. Repeat the same process, S3 equal to minus gradient of F3, and which is now minus 0.2, comma 0.2. Put these values, get the next optimum value of your step length in search direction S3. So in order to get the step length in search direction S3, you will have these values x3 plus lambda 3 plus s3 is equal to this. If you put these values, the values will come minus 0.8 minus 0.2 lambda 3 comma 1.2 plus 0.2 lambda 3, which will be equal to this expression. Okay, 0.04 lambda 3 square plus 0.08 lambda 3 minus 1.2 0. So for calculating the optimum value, what you will do, you will again take derivative of this function and equate it equal to 0. So here lambda 3, again it is coming equal to lambda 3 equal to 1.0. Okay, so here again you will calculate the value of your next optimum point, which will be x4. So x4 x4 is equal to x3 plus lambda 3 s3, and this value will be, now this will become minus 1.0, 1.4. Okay, so I hope you are able to follow these steps, how we are doing repeated iterations. And here you can see that after iteration number 3, if you are getting the value of x4, And if you again check the gradient at of function at x4, you are getting these values minus 0.20 comma minus 0.20, which is again non-zero, which is not 0 comma 0. So you will further go for further step, that is step iteration number 4, and you will search, your next search direction will be minus gradient of f4. Okay, so I have put in this particular example up to iteration number 3. You can calculate up to even more than that until you get your gradient equal to 0 comma 0. Okay, so since we were knowing the solution of this particular problem from the previous example, so I have put the values. Otherwise, you need to move further, maybe for iteration number 4 or 5, you are able to get the accurate solution of your this given function using your CPEST descent method. Okay, so since I have cut short this method in a very short, if there are any query, you can ask. Otherwise, we will stop here, and we have some time to take your queries. I have already uploaded the lecture note of this particular lecture. You can solve this, at least you practice this equation, this problem using your CPEST descent method. And if you are facing any difficulty, I am available online. I will not close this meeting. Okay, so you can practice using this problem. If there is any query, we can take. Okay. So this question, you are talking about this particular question, or yes, general. Okay. So I will be sharing questions in the form of assignments. Okay. Yeah.